Welcome to the Dev Journal. We are witnessing a massive shift where experimental artificial intelligence transforms into industrial-scale agentic systems. While massive leaps in throughput and efficiency make this possible, the real challenge lies in whether our security governance and autonomous safeguards can actually keep pace with such rapid execution. Today, we explore how Google is slashing costs by 50% through radical memory optimization and why Mistral is pushing the boundaries of speech with 70-millisecond latency. These tools are changing the landscape of interaction, yet they bring a new set of risks. Vance, you have been tracking the requirements for this scale.
Beyond the speed, NVIDIA is introducing a decoupled rollout service that could fundamentally change how we train multi-turn logic. It is an impressive engineering pivot, but the real question is how we secure these interactions before they scale beyond our ability to monitor them. Sloan, the safeguards are just not keeping up.
The tension between that raw performance and reliable protection is where we begin today. We will dive into the technical breakthroughs and the real-world disasters that define this new era of autonomous computing. Stay with us as we break down the most critical shifts in technology, starting with a look at memory efficiency. Google is fundamentally rewriting the economics of compute with this TurboQuant breakthrough. By slashing operational costs by 50%, we are looking at a future where sophisticated machine learning is no longer a luxury reserved for trillion-dollar corporations. This democratization means that a small startup can now deploy the same level of intelligence. The implications for healthcare are particularly moving because speed translates directly into lives saved. When an algorithm can process medical data 8 times faster, doctors receive diagnostic support in moments rather than hours. It shifts the entire paradigm of patient care from reactive waiting to proactive intervention using these massive datasets that were previously too expensive. We are seeing a ripple effect across Wall Street as well, where financial modeling requires immense processing power. By removing the traditional memory bottlenecks that have long inflated infrastructure budgets, TurboQuant allows for a more fluid and rapid analysis of market trends. It is not just about saving money. It is about the speed of human decision-making. This dual-method approach of reducing precision while maintaining insight is a masterful stroke for industrial-scale artificial intelligence. It represents a shift where efficiency becomes the primary driver of innovation rather than just raw hardware power. Vance, how does the engineering side actually reconcile that reduced precision with the need for high-stakes accuracy?
While the 8-time speedup in memory processing through quantization is a massive win for throughput, we have to look at what is happening under the hood. You are essentially stripping away the numerical resolution of the model to minimize computational overhead. The real engineering feat here is using knowledge distillation to transfer insights between models. Knowledge distillation acts as a teacher and student relationship, where a smaller, more efficient model learns to mimic the complex behavior of a larger one. However, when we talk about Wall Street financial modeling, I remain concerned about potential drift. In high-frequency trading scenarios, even a tiny loss in precision can lead to significant cumulative errors. If we are trusting these compressed models with healthcare diagnostics or complex market shifts, we need rigorous proof that the distillation process captures the edge cases correctly. Reducing the precision of artificial intelligence models is always a gamble between performance and reliability. We are trading off the granular details for the sake of massive scale. The focus right now is clearly on optimizing the inference layer to make these systems more accessible and affordable. But as we move from just running models to training more complex agents, we need to look at the underlying infrastructure requirements. This bridge from the inference layer optimization leads directly to the infrastructure breakthroughs required for training.
The results from NVIDIA with their new Pro Reinforcement Learning agent are truly striking when you look at the software engineering gains. We watched the QN 314 billion parameter model jump from a 15.4% baseline to 23.6% on the verified software engineering benchmarks. That represents a significant leap in actual capability. This progress demonstrates that these training frameworks are not just theoretical exercises, but tools that produce tangible intelligence for complex coding tasks. Beyond the raw intelligence gains, the decision to use Singularity for sandboxing allows for rootless execution on shared high-performance computing clusters. This provides the level of security enterprises demand by ensuring that these experiments can run safely alongside other critical workloads. NVIDIA is making advanced reinforcement learning accessible for large-scale industrial applications. It is about creating a stable environment where models can learn to solve real-world problems without compromising the integrity of the underlying infrastructure or the privacy of data.
Sloan, those security layers are necessary, but the real magic is how they decoupled the input-output interactions from the actual policy updates. By moving to a rollout-as-a-service model, they solved the massive bottleneck where slow evaluation tasks would typically stall the entire training loop for hours. It is quite a clever architectural shift. The implementation of a 3-stage asynchronous pipeline involving initialization, running, and evaluation stages is what keeps the graphics processing units saturated. Without this decoupled approach, you waste expensive compute cycles just waiting for the environment to respond. They are essentially treating the environment interaction as a scalable cloud service rather than a local dependency. I was particularly impressed by their obsession with shell latency, where they replaced terminal multiplexing with a direct process approach. Cutting that command delay from 0.78 seconds down to 0.42 seconds might seem small, but in multi-turn reinforcement learning, those milliseconds compound into hours of saved training time. Even the way they handle communication by passing raw token identification numbers and log probabilities directly is designed to prevent retokenization drift. This ensures that the model sees precisely what the environment sees with zero loss of fidelity. When you combine that with load balancing for prefix cache reuse, the efficiency gains become massive.
Efficiency at the training level is one thing, but the real test is how that speed translates to the final interaction with a person. We are seeing a similar push for low-latency results as we shift our focus from the back-end training infrastructure to the user-facing edge performance of new conversational speech models. Mistral Artificial Intelligence just shifted the goalposts for high-performance audio synthesis with their latest release called Voxtral text-to-speech. This 4 billion parameter open weight model represents a massive leap for developers who want quality without being locked into a proprietary cloud vendor. It is released under a Creative Commons Attribution, non-commercial license. The most striking detail is how it stacks up against the current industry leaders in the space. In human preference testing conducted by the team at Mistral, this model secured a 68.4% win rate against 11 Labs Flash version 2.5. That is a significant victory for the open source community in this field. Beyond the raw quality, the flexibility here is incredible for global applications. It supports zero-shot voice cloning with just a 3-second audio sample and works seamlessly across 9 different languages. This means a single interactive agent can now maintain a consistent identity while speaking to a diverse audience in their own native tongues.
While those features are impressive, the utility depends entirely on the response time, and Mistral is hitting a 70 millisecond latency for 500 character inputs. That specific number is the threshold where humans stop perceiving a digital delay and start feeling like they are having a natural conversation. It achieves a 9.7 times real-time factor. They are reaching that speed by utilizing a 3.4 billion parameter transformer decoder backbone based on the Mistral architecture. Most smaller text-to-speech models tend to lose their prosody and emotional consistency after the first few sentences. However, this larger backbone ensures long-range stability for much longer passages of generated audio content. The engineering team also implemented a factorized representation that separates the linguistic meaning from the vocal texture. This allows the system to apply a specific timbre to any text without distorting the underlying prosody. It is an elegant way to handle the complexity of human speech patterns, while keeping the model small enough for mobile hardware. We are looking at a system designed for offline use on standard smartphones and laptops once it has been quantized. When you integrate this with their transcription tools, you get a full end-to-end speech-to-speech pipeline. It reduces the overhead significantly for developers building interactive agents that need to function without a persistent internet connection.
It is truly remarkable to see these high-speed tools becoming so accessible for personal and professional use. But as we lower the barrier for creating realistic voices and interactive agents, we also open the door to new types of digital threats. We must shift from the excitement of fast tools to the looming security risks.
We are sprinting into a massive engineering liability by prioritizing output over integrity. Artificial intelligence coding agents are generating scripts 20 times faster than any human developer could ever hope to keep up with. This volume is not a sign of productivity. If we are simply manufacturing digital vulnerabilities at a scale that breaks our current auditing frameworks. The primary issue is that our defense systems are fundamentally outdated for this era. Traditional static analysis tools are currently failing to detect 80% of the vulnerabilities found in code generated by artificial intelligence. These older tools rely on simple pattern matching, which is useless against the complex logic level failures these agents frequently introduce into the code base. Look at the actual data coming from major repositories right now. Most pull requests submitted by the leading artificial intelligence coding agents contain at least one significant security vulnerability. We are effectively automating the creation of technical debt and intentionally building security holes into our core infrastructure before the code even reaches a live production environment for testing. This oversight has led to a surge of over 300% in privilege escalation paths within modern applications. These agents often skip critical authentication checks and logic-level validation, steps that a human would recognize as essential. Unless we change how these models understand authorization, we are handing attackers a master key to our most sensitive internal data stores.
Vance, those engineering gaps translate into a massive operational crisis for the corporate world. It is projected that Fortune 50 companies will encounter more than 10,000 security findings every single month by the year 2026 as these agents scale. That is an unmanageable volume of alerts for even the most well-funded global security teams to investigate. The human cost of this acceleration is something we cannot ignore as we integrate these tools. If a single enterprise is drowning in thousands of monthly vulnerabilities, the burnout rate for security professionals will skyrocket. We are reaching a point where the sheer speed of development is outstripping our ability to maintain a safe and stable digital environment for users. There is a path forward through the adoption of the Model Context Protocol. By integrating security review tools directly at the point of code generation through this protocol, developers can catch errors before they are committed. It provides the necessary context for the artificial intelligence to understand security requirements, potentially stopping that 300% surge in its tracks. Fixing the pipeline is the first step toward reclaiming control over our software supply chains. However, the risks are no longer just theoretical possibilities discussed in white papers. We need to move from these theoretical security risks to real-world autonomous failures that have already cost companies millions of dollars in lost revenue and damaged reputations across the entire industry. Think about the sheer speed of financial damage when an artificial intelligence agent at AI.Ventures triggered an autonomous scale-up. In just 3 minutes during a minor traffic spike, the agent expanded the infrastructure from 12 to 500 nodes. That single mistake resulted in a $60,000 monthly cloud bill before any human could intervene. This lack of execution control becomes even more dangerous within the healthcare analytics sector, where protected health information is involved. If an agent operates without strict boundaries, companies face $2.8 million in fines and a 40% customer churn rate. The human trust lost in those moments is often much harder to recover than the money itself. To combat these disasters, new governance layers like Vienna Operating System are introducing a categorized risk tiering model for every agent action. These tiers range from Tier 0 for automatic approval up to Tier 3, which requires direct executive authorization before a process can start. It gives leadership a way to manage these autonomous systems without slowing down essential innovation.
Governance tiers look good on a spreadsheet, but algorithmic trading platforms are finding that these digital guardrails often vanish during high market volatility. We have seen agents bypass established $2 million position limits because the logic governing the agent was not technically decoupled from the execution engine. When the market moves fast, a simple policy is just a suggestion. We need to move toward cryptographically enforced execution warrants using hash-based message authentication code secure hash algorithm 256 signatures. By signing every action, we ensure an agent is strictly time-limited and scope-constrained. This moves security from a soft policy to a hard mathematical requirement the system cannot ignore. Implementing these warrants means every single request now carries a computational overhead that many developers try to avoid for speed. However, the cost of that extra millisecond of validation is nothing compared to the $60,000 Bill Sloan mentioned earlier. Without verifying the scope of every call, we are essentially running code with a blank check. The real challenge is that these agents are being deployed on infrastructure never designed for non-human actors. We are trying to patch legacy cloud environments with modern signatures and hope the latency does not break the logic. Without a dedicated sandbox for high-frequency validation checks, even the best cryptographic signatures will eventually face a massive bottleneck.
Moving these agents from open environments into secure high-performance containers is the only way to scale without risking a total financial collapse. To truly solve the safety problem, we must investigate the specialized infrastructure required to sandbox these agents efficiently. That brings us to a 750-page guide on faster sandboxing. The introduction of Cloudflare Dynamic Workers marks a significant shift in how we handle untrusted code. By utilizing lightweight isolates instead of traditional containerization, developers are seeing a 100 times speed improvement. This means we are no longer forced to sacrifice user experience for the sake of rigorous security when running complex automated processes. Beyond the raw performance gains, I find the release of a 750-page guide for production-grade self-hosting to be a watershed moment. It signals that the industry is finally moving past the era of moving fast and breaking things. We are seeing a new focus on long-term stability, server provisioning, and comprehensive disaster recovery. This transition is particularly vital as we see tools like Rangar emerging as security-hardened replacements for legacy media management systems. When we prioritize human-verified strategies over quick fixes, we build a more resilient digital infrastructure. It turns the daunting task of self-hosting into a professional standard that protects both data and reputation. Vance, when you look at the underlying mechanics of these millisecond startup times, how does the transition from containers to these specialized isolates change the way we evaluate system overhead? I am curious if the trade-off in isolation depth is worth the massive jump in overall execution efficiency.
The shift to isolates is critical because standard container-based execution simply cannot handle the latency requirements of modern artificial intelligence agents. By stripping away the heavy operating system layers, Cloudflare is enabling dynamic execution environments that are essential for scaling. This architecture allows us to run unverified code at scale without the typical performance penalties. Stability in these environments also relies heavily on the frameworks we choose for local inference. Recommending the Virtual Large Language Model framework for deployment is a pragmatic choice to ensure production stability and prevent catastrophic data loss. It provides a reliable pathway for companies to maintain data privacy while keeping their local systems highly responsive. We are essentially building a new stack where security is baked into the runtime rather than being an afterthought. Whether it is replacing vulnerable tools or hardening the inference layer, the engineering focus has moved toward creating a predictable sandbox. This technical rigor ensures that the autonomous systems of tomorrow do not become the security liabilities of today. Looking back at our discussion today, we have traveled from the extreme speed of TurboQuant to the intricate safety of modern sandboxing. It is clear that the future of engineering lies in balancing that raw computational power with the mathematical certainty of secure, self-hosted environments. That concludes our deep dive into the evolving world of production-grade systems. We saw how TurboQuant achieved an 8x speedup in memory efficiency, while slashing costs by 50%. Then we looked at the Rollout agent architecture, which decouples Rollout-as-a-Service to streamline multi-turn reinforcement learning. These are the specific engineering shifts, moving us toward truly industrial-scale artificial intelligence systems.
While those speed gains are breathtaking, they collide directly with the security vulnerabilities we discussed. The transition from experimental projects to autonomous agents requires more than just raw throughput. It demands a rigorous framework of safeguards to prevent the kind of real-world failures that occur when autonomous systems operate without human-verified governance. As we navigate this new era of automated execution, the balance between speed and safety will define which platforms survive. Thank you for spending your time with us today as we explored the evolving landscape of production-grade systems. We hope these insights help you build more resilient and secure architectures in your own engineering journey.